Hi everybody. So in this class so far, we've been studying linear systems of equations, which can be expressed concisely in the form of a matrix equation, ax equals b, and we know how to solve these equations using Gauss-Jordan elimination. So you might think we're done with that. We've learned how to solve them. Let's move on to the next thing. But there's more interesting ideas here if you think about not just what the solutions are, but how they're related to each other. And in this lecture, we're going to learn about one of the most important principles that's along these lines. So first of all, let's consider a really special case of these linear systems, the case where b is equal to 0. And I'll just point out that that 0, we just write 0, but we're really talking about the 0 vector, which is the vector that has all zeros in it. Sometimes for emphasis, people will write a little arrow on top of the 0 to indicate it's a 0 vector. You'll see it either way, and you should just be comfortable seeing it either way. So anyway, the equations we're looking at are equations of the form ax is equal to 0. And these equations are called homogeneous equations. So what can we say about homogeneous equations? Well, one thing we can say is that these systems are always consistent. There always is a solution. And that's because you could just set x to be equal to 0. And if you set x to be equal to 0, then it doesn't matter what a is. A times 0 is going to be 0. Yeah, but it's kind of a boring solution, right? So there's a technical mathematical word that's used whenever something is boring. And that word is trivial. So in this case, we would say that x equals 0 is the trivial solution. And so then you could ask a follow-up question. Are there non-trivial solutions? Okay, so let's think about what would have to happen for there to be non-trivial solutions. This is something that fits into our general theory that we've already discussed. And what we've learned is that when you have an equation of the form ax equals b, there's either 0 solutions, 1 solution, or infinitely many solutions. And in this case of a homogeneous equation, we know that there's at least one solution, which is the trivial one. And if there is one solution, that has to be it. So if there are non-trivial solutions, you have to be in the case where there are infinitely many solutions, which is the case where you have free variables. So for example, if you plug in the matrix and get the reduced echelon form to look like this, then there are no free variables, and the trivial solution is the only one. So here's another example. Suppose this was your reduced echelon form. If you turn this back into a system of equations, then you get x1 plus 2x2 is equal to 0, x3 is equal to 0, and x4 is equal to 0, and we know that we can set x2 to be a free variable. So if we set x2 to be equal to t, then we get x1 is equal to minus 2t, and x3 and x4 are equal to 0. And we can rewrite the solution as a vector, and in this vector we can actually factor the t out. And so we see that the solutions are all just multiples of this one vector, minus 2, 1, 0, 0. And you can take different multiples, which is what the different t-values would give you, and you'd get different solutions. So that's already kind of cool when you think of it as just multiples of a vector. And then if you think of it geometrically, then that's also interesting because that's like a line going through the origin, right? If t is equal to 0, then you're at the origin. And then when t has non-zero values, then you get different points on this line that's exactly the line that's determined by this vector, minus 2, 1, 0, 0. So this example that we just did is actually illustrative of the general case. If you have a homogeneous equation with one free variable, the solution set always looks like x equals t times some constant vector. And if you have two free variables, then you can always write your solution in a form that looks like this, which we can now interpret as x being a linear combination of these two vectors v1 and v2. And probably at this point you can guess what happens if there's 3 or 4 free variables, or more. But the most interesting thing happens when you compare non-homogeneous equations with homogeneous equations. So let's go back to this example that we did earlier in the case of a homogeneous equation, But instead of having zeros on the right-hand side, let's put a different vector that's not 0 on the right-hand side. In this case, 3, 1, 4. So if this was your reduced echelon form, what would the solutions look like? Well, we can basically follow the same steps that we did before, but with the 3, 1, 4 on the right-hand side. And so we'd again set x2 to be equal to t. And so then when we write the solution in vector form, we can't just factor a t out, but what we can do is we can separate it into two terms, where one term doesn't have t, and the other term does have t, and we can factor the t out there. And so this is what you end up with, that x is 3, 0, 1, 4 plus t times minus 2, 1, 0, 0. And the thing that's really interesting here is that the part that has the t is the homogeneous solution. And that is exactly where the ambiguity in the solution lies, right? You can pick different values of t and you get different solutions. It's the homogeneous part of the solution that's changing when you do that. The other part of the solution can be called the particular solution because it is a particular solution. And what I mean by that is that you're allowed to set t to be equal to 0, and if you do, then this is what you're left with. So this is a solution. 3, 0, 1, 4 is a solution to the system. And then you can get different solutions by adding different homogeneous solutions. So here's a theorem that encapsulates the idea that we've just been discussing. If x equals p is one solution to the equation ax equals b, then every other solution is of the form x equals p plus h, where x equals h is a solution to the homogeneous equation ax equals 0. So in other words, the general solution to the equation, which is to say the set of all solutions, can be obtained by taking one particular solution and adding all the different homogeneous solutions. General equals particular plus homogeneous. So if you were to implement this theorem in terms of solving the equation ax equals b, this is what you would do. The first thing you do is you'd find a particular solution p. The second thing you would do is you would solve the homogeneous equation ax equals 0. And then finally, you would add the answers to 1 and 2 to get the general solution to ax equals b. All right, now hold up. You're not actually going to do this. The Gauss-Jordan elimination method gives you the whole answer already, and you don't need to do all this. But what you can do is you can recognize that when you get your solution from Gauss-Jordan elimination, that it has this form automatically. This automatically happens. And by recognizing it as having this form, you can understand the solution better. And we'll be talking more about how this helps you to understand it later. Okay, but before I end, I want to give you a little preview of what's to come, because I feel like this general equals particular plus homogeneous principle is possibly the most important concept in the class. And it's hard to really recognize why it's so important based on what we've just been talking about in terms of systems of linear equations. So I feel like I need to give you a little preview of what's to come. So later in the class, we're going to interpret linear equations more generally in a setting where instead of just vectors, you might be talking about functions. And instead of matrices, you could have something like a derivative. So an example of an equation like this would be d dx of f of x is equal to x squared. So when you're solving this equation, you're trying to find the set of all functions, f of x, such that when you take the derivative, you get x squared. Now, you have almost certainly solved equations like this before in your calculus class. And what I want you to do is just think about how you solve it. What happens? Well, the first step is that you just find a solution. Call it the power rule, call it trial and error, whatever. You find a solution, and probably the one that you're going to find is x cubed over 3. Because x cubed over 3 does have this property that when you take its derivative, you get x squared. so it is a solution. And then what do? Well, you add plus c. You'll notice that I wrote this as step 3 because really what's happening in your calculus class is that you skip straight to step 3. But there is a middle step, which is that you solve the homogeneous equation where d dx of f of x is equal to 0. And what are the functions whose derivative is equal to 0? Those are the constant functions. And so when you add that plus c, what you're really doing is you're adding the particular solution, x cubed over 3, to the homogeneous solution, which is c. And when you add those two together, you get the general solution to the original equation. So, we'll talk about this later, but hopefully this gives you some appreciation for this principle of general equals particular plus homogeneous. Because in this scenario where you're solving an equation involving derivatives, you can't use Gauss-Jordan elimination because you don't have matrices anymore. So this is the principle that allows you to solve the equation. And in fact, this is the principle that you were using in your calculus class, but you just didn't realize it.